All right, so welcome back to the series on machine learning. I'm gonna be preparing for the discussion I'll have it um, on Monday. So I need to get through lesson 4, which is gonna have information from chapter 3, from various chapters throughout the book. The video lessons don't go through the book in chronological or in sequential order. They kind of skip around from chapter to chapter. But our main thing we're going to be focusing on is this questionnaire, getting that done today, and just getting the whole video watched. Usually the videos are multiple hours long, so that in and of itself is kind of a feat. Yeah, so this is a 2 hour long video, so let's try to get at least an hour of this watched now. And then go back and do the questions, and then yeah. So let's try to get at least an hour of this video watched right now.
Welcome back, and here is lesson 4, which is where we get deep into the weeds of exactly what is going on when we are training a neural network. And we started looking at this in the previous lesson. We were looking at stochastic gradient descent. And so to remind you, we were looking at what Arthur Samuel said. Suppose we arrange for some automatic means of testing the effectiveness of any current weight assignment, or what we call parameter assignment, in terms of actual performance, and provide a mechanism for altering the weight assignment so as to maximize that performance. So we could make that a time automatic, and a machine so programmed would learn its experience. And that was our goal. So our initial attempt on the MNIST dataset was not really based on that. We didn't really have any parameters. So then last week, we tried to figure out how we could parameterize it, how we could create a function that had parameters. And what we thought we could do would be to have something where, say, the probability of being some particular number was expressed in terms of the pixels of that number, and some weights, and then we would just multiply them together and add them up. So we looked at how stochastic gradient descent worked last week, and the basic idea is that we start out by initializing the parameters randomly. We use them to make a prediction using a function such as this one. We then see how good that prediction is by measuring using a loss function. We then calculate the gradient, which is how much would the loss change if I changed one parameter by a little bit. We then use that to make a small step to change each of the parameters by a little bit, by multiplying the learning rate by the gradient, to get a new set of predictions. And so we went round and round and round a few times, until eventually we decided to stop. And so these are the basic 7 steps that we went through. And so we did that for a simple quadratic equation. And we had something which looked like this. And so by the end, we had this nice sample of a curve getting closer and closer and closer. So I have a little summary at the start of the section, summarizing gradient descent, that Sylvain and I have in the books in the book, of what we just did. So you can review that and make sure it makes sense to you. So now let's use this to create our MNIST 3s versus 7s model. And so to create a model, we're going to need to create something that we can pass into a function like, let's see where it was, pass into a function like this one. So we need just some pixels that are all lined up and some parameters that are all lined up, and then we're going to sum them up. So our x's are going to be pixels. And so in this case, because we're just going to multiply each pixel by a parameter and add them up, the fact that they're laid out in a grid is not important. So let's reshape those grids and turn them into vectors. The way we reshape things in PyTorch is by using the view method. And so the view method, you can pass to it how large you want each dimension to be. And so in this case, we want the number of columns to be equal to the total number of pixels in each picture, which is 28 times 28, because that's the 28 images. And then the number of rows will be however many rows there are in the data. And so if you just use -1, when you call view, that means as many as there are in the data. So this will create something of the same total number of elements that we had before. So we can grab all our 3s, we can concatenate them with all of our 7s, and then reshape that into a matrix where each row is one image with all of the rows and columns of the image all lined up in a single vector. So then we're going to need labels. So we're going to need labels. Our labels will be a 1 for each of the 3s and a 0 for each of the 7s. So our basically what we created is 3 model. So that's going to create a vector. We actually need it to be a matrix in PyTorch. So unsqueeze will add an additional unit dimension to wherever I've asked for, so here in position 1. So in other words, this is going to turn it from something which is a vector of 12,396 long into a matrix with 12,396 rows and 1 column. That's just what PyTorch expects to see. So now we're going to turn our x and y into a dataset. And a dataset is a very specific concept in PyTorch. It's something which we can index into using square brackets. And when we do so, it's expected to return a tuple. So here, if we look at, we're going to create this dataset, and when we index into it, it's going to return a tuple containing our independent variable and independent variable for a particular row. And so to do that, we can use the Python zip function, which takes one element of the first thing and combines it with, concatenates it with one element of the second thing, and then does that again and again and again. And so then we can create a list of those. It gives us a dataset. It gives us a list, which when we index into it, it's going to contain one image and one label. And so here you can see y, there's my label, and my image, I want to contain the whole thing, it's a 724 long vector. So that's a really important concept. A dataset is something that you can index into and get back a tuple. And here I am, this is called destructuring the tuple, which means I'm taking 2 parts of the tuple and putting the first part in one variable and the second part in the other variable. Which is something we do a lot in Python, it's pretty handy, a lot of other languages support that as well. We get the same 3 steps for a validation set. So we've now got a training data set and a validation data set. Right, so now we need to initialize our parameters. And so to do that, as we discussed, we just do it randomly. So here's a function that given some size, some shape if you like, we'll randomly initialize using a normal random number distribution. PyTorch is what random does, and we can hit Shift Tab to see how that works. Okay. And it says here that it's going to have a variance of 1. So I probably should call this standard deviation. I probably should call this variance, actually. So multiply by the variance to change its variance to whatever is requested, which will default 1. And then as we talk about when it comes to calculating our gradients, we have to tell PyTorch which things we want gradients for. And the way we do that is require spread underscore. Remember this underscore at the end is a special magic symbol which tells PyTorch that we want this function to actually change the thing that it's referring to. So this will change this tensor such that it requires gradients. So here's some weights. So our weights are going to need to be 28 by 28 by 1 shape. 28 by 28 because every pixel is going to need a weight. And then 1 because we're going to need to get that unit access into a column. So that's what PyTorch checks. So there's our weights. Now, just weights by pixels actually isn't going to be enough because weights by pixels will always equal 0 when the pixels are equal to 0. It has a 0 intercept. So we really want something which is like w weights plus b line. So the b is we call the bias, and so that's just going to be a single number. So let's grab a single number for our bias. So remember I told you there's a difference between parameters and weights, strictly speaking. So here the weights are the w in this equation, the bias is b in this equation, and the weights and bias together is the parameters of the function. They're all the things that we're going to change, they're all the things that have gradients that we're going to update. So this is an important bit of diagram for you. The weights and biases of the model are the parameters. So we can, yes, question?
What's the difference between gradient descent and stochastic gradient descent?
So far we've done gradient descent, we'll be doing stochastic gradient descent in a few minutes. So we can now create a calculated prediction for one image, so we can take an image such as the first one and multiply by the weights. We need to transpose them to make them line up in terms of the rows and columns, and add it up, and add the bias, and there is a prediction. We want to do that for every image. We could do that for all, and that would be really slow. It wouldn't run on GPU, and it wouldn't run in optimized C code. So we actually want to use always to do kind of like looping over pixels, looping over images. You always need to try to make sure you're doing that without Python logic. In this case, doing this calculation for lots of rows and columns is a mathematical operation called matrix multiply. So if you've forgotten your matrix multiplication, or maybe you've got around to it in high school, it would be a good idea to have a look at Khan Academy or something to learn about what it is, but it's actually I'll give you the quick answer. This is from Wikipedia. If these are two matrices A and B, then this element here, 1, 2, in the output, is going to be equal to the first bit here times the first bit here plus the second bit here times the second bit here. So it's going to be B12 times A11 plus B22 times A12. That's you can see the orange, matches the orange. Ditto for over here. This would be equal to B13 times A31 plus B23 times A32, and so forth for every party. Here's a great picture of that in action. You look at matrix multiplication.xyz. Another way to think of it is we can kind of flip the second bit over on top, and then multiply each bit together and add them up. Multiply each bit together and add them up. And you can see always the second one here ends up in the second spot, and the first one ends up in the first spot. And that's what matrix multiplication is. So we can do our multiply and add up by using matrix multiplication. And in Python, and therefore PyTorch, matrix multiplication is the @ operator. So when you see that means matrix multiply. So here is our 20.2336. If we do a matrix multiply of our training set by our weights, and then we add bias. And here's our 20.36 for the first one. And you can see that it's doing every single one. Okay. So that's really important, is that matrix multiplication is an optimized way to do these simple linear functions for as many kind of rows and columns as we want. So this is one of the two fundamental equations of any neural network. Some rows of data, rows of columns of data, multiply some weights, add some bias. And the second one we see in a moment is an activation function. So that is the predictions from our randomly initialized model. So we can check how good our model is. And so to do that, we can decide that anything greater than 0 we will call a 3, and anything less than 0 we will call a 7. So preds greater than 0 tells us whether or not something's predicted to be a 3 or not. Then turn that into a float, so rather than true or false, 1 0, that's what our training set contains. And then check whether our threshold predictions are equal to our training set. And this will return true every time a row is correctly predicted and false otherwise. So if we take all those trues and falses and turn them into floats, so that 1s and 0s, and then take their mean, it's 0.49. So not surprisingly, our randomly initialized model is right about half the time at predicting 3 supersets. I add one more method here, which is .item. Without .item, this would return a tensor. It's a rank 0 tensor. It has no rows, it has no columns, it's just a number on its own. But I actually want to unwrap it to create a normal Python scalar, mainly because I want to easily see the full set of decimal places. And the reason for that is I want to show you how we're going to calculate the derivative on the accuracy by changing the parameter by a tiny bit. So let's take one parameter, which will be weight 0, and multiply it by 1.0001. And so that's going to make it a little bit bigger. And then if I calculate how the accuracy changes based on the change in that weight, that will be the gradient of the accuracy with respect to that parameter. So I can do that by calculating my new set of predictions, and then I can threshold them, and I can check whether they're equal to the training set, and then take a mean, and I get back exactly the same number. So remember that gradient is equal to rise over run. If you remember back to calculus, or if you've forgotten your calculus, hopefully you reviewed it in Khan Academy. The change in the y, so y new minus y old, which is 0.4912, etc., minus 0.4912, etc., which is 0, divided by this change, will give us 0. So at this point we have a problem. Our derivative is 0, so we have 0 gradients, which means our step will be 0, which means our prediction will be unchanged. Okay, so we have a problem. And our problem is that our gradient is 0, and the gradient of 0, we can't take a step, and we can't get better predictions. And so, intuitively speaking, the reason that our gradient is 0 is because when we change a single pixel by a tiny bit, we might not ever in any way change an actual prediction to change from a 3, predicting a 3 to a 7, or vice versa, because we have this threshold. Okay, and so in other words, our accuracy loss function here is very bumpy. It's like flat step, flat step, flat step. So it's got this 0 gradient all over the place. So what we need to do is use something other than accuracy as our loss function. So let's try and create a new function. And what this new function is going to do is it's going to give us a better value, kind of in much the same way that accuracy gives a better value. So this is a loss. Remember, a small loss is better. So it'll give us a lower loss when the accuracy is better, but it won't have a 0 gradient. So it means that a slightly better prediction needs to have a slightly better loss. So let's have an example. Let's say our targets, our labels, of like the is 3. There's 3 rows, 3 images here. 1, 0, 1. Okay. And we've made some predictions from neural net, and those predictions gave us 0.9, 0.4, 0.2. So now, consider this loss function. A loss function, we're going to use torch.where, which is basically the same as this list comprehension is basically an if statement. So it's going to say for where target equals 1, we're going to return 1 minus predictions. So here target is 1, so it'll be 1 minus 0.9. And where target is not 1, it will just be predictions. So for these examples here, the first one target equals 1 will be 1 minus 0.9, 0.1. The next one is target equals 0, so it will just be the prediction, which is 0.4. And then for the third one, it's a 1 for target, so it will be 1 minus prediction, which is 0.8. And so you can see here, when the prediction is correct, in other words, it's a high number when the target is 1, and a low number when the target is 0, these numbers are going to be smaller. So the worst one is when we predicted 0.2, so we really thought that was actually a 0, it's actually a 1, so we ended up with 0.8 here, because this is 1 minus prediction, 1 minus 0.2 is 0.8. So we can then take the mean of all of these to calculate a loss. So if you think about it, this loss will be the smallest if the predictions are exactly right. So if we did predictions is actually identical to the targets, then this will be 0, 0, 0. Okay? Whereas if they were exactly wrong, let's say they were 1 minus, then it's 1, 1, 1. So it's going to be, the loss will be better, i.e. smaller, when the predictions are closer to the targets. And so here we can now take the mean, and when we do, we get here 0.433. So let's say we change this last bad one, this inaccurate prediction, from 0.2 to 0.8. then the loss gets better from 0.43 to 0.23. So this is just this function, this torch.where.me. So this is actually pretty good. This is actually a loss function, which pretty closely tracks accuracy, which the accuracy is better, the loss will be smaller. But also, it doesn't have these zero gradients, because every time you change the prediction, the loss changes, because the prediction is literally part of the loss. That's pretty neat, isn't it? One problem is, this is only going to work well as long as the predictions are between 0 and 1. Otherwise, this one-line prediction thing is going to look funny. So we should try and find a way to ensure that the predictions are always between 0 and 1. And that's also going to make a lot more intuitive sense, because we like to kind of think of these as if they're like probabilities, or at least nicely scaled numbers. So we need some function that can take our numbers, look. Something which can take these big numbers and turn them all into numbers between 0 and 1. And it so happens that we have exactly the right function. It's called the sigmoid function. So the sigmoid function looks like this. If you pass in a really small number, you get a number very close to 0. If you pass in a big number, you get a number very close to 1. It never goes past 1, and it never goes smaller than 0. And then it's going to have a smooth curve between. And in the middle, it looks a lot like the way of x1. This is the definition of the sigmoid function. It's 1 over 1 plus e to the minus x. What is x? X is just e to the power of something. So if we look at e, it's just a number by pi. It's just a number that has a particular value. Right? So if we go e.
Okay, I'll admit. So obviously, I'm having trouble paying attention to this. Kind of zoned out, looking at other things, not really paying close attention. It's just a lot for me to do, and it's like, you know, I'm going to pay more attention to the second part of it.
Squared, and look at it's going to be a tensor. Use PyTorch.
It's just kind of hard because personally, I don't find machine learning really that interesting. I think it's important, but like amateur do-it-yourself machine learning, I just don't think has a lot of value. Computer vision, I would say yes, but like machine learning, deep learning, like not really, unless it's paired with computer vision. Like computer vision, like, you know, I'm working on a application for that right now. I haven't worked on it in forever, but like I would love to learn more about computer vision, but I'm just not sure that deep learning is going to be relevant to me that much.
Make it a float. There we go. Okay, you can see that these are the same number. So that's what torch.x means. Okay, so you know, for me, when I see these kinds of interesting functions, I don't worry too much about the definition. What I care about is the shape. Right, so you can have a play around with graphing calculators or whatever to kind of see why it is you end up with this shape from this particular equation. But for me, I just don't think about that. It never really matters to me. What's important is the sigmoid shape, which is what we want. It's something that squashes every number to be between 0 and 1. So we can change m's loss to be exactly the same as it was before, but first we can make everything into sigmoid first, and then use torch.where. So that is a loss function that has all the properties we want. It's something which is going to not have any of those nasty 0 gradients, and making sure that the input to the where is between 0 and 1. So the reason we did this is because our accuracy was kind of what we really care about is word accuracy. We can't use it to get our gradients, just to create a step to improve our parameters. So we can change our accuracy to another function that is similar in terms of it's better when the accuracy is better, but it also does not have these 0 gradients. And so you can see now why we have a metric and a loss. The metric is the thing we actually care about. The loss is the thing that's similar to what we care about, that has a nicely behaved gradient. Sometimes the thing you care about, your metric, does have a nicely defined gradient, and you can use it directly as a loss. For example, we often use mean squared error, but for classification, unfortunately not. So we need to now use this to update parameters. And so there's a couple of ways to do this. One would be to look through every image, calculate a prediction for that image, and then calculate a loss, and then do a step, and then step for what are the parameters, and then do that again for the next image, and the next image. That's really slow, because we're doing a single step for a single image. So that would mean epoch would take a while. We could go much faster by doing every single image in the dataset. So big matrix multiplication, not parallelized in GPU, and then so then we can then do a step based on the gradients looking at the entire dataset. But now it's going to be like a lot of work to just update the weights once. Remember, sometimes our datasets have millions or tens of millions of items, but that's probably a bad idea too. So what optimize? Let's grab a few data items at a time to calculate our loss and our step. If we grab a few data items at a time, those few data items are called a mini-edge. And mini-edge just means a few pieces of data. And so the size of the mini batch is called surprising mini batch size. Right? So the bigger the batch size, the closer you get to the full size of your data set, the longer it's going to take to calculate a single set of losses, a single step. But the more accurate it's going to be. It's going to be like the gradient's going to be much closer to the true data set gradients. And in the smaller batch size, the faster each step will be able to do, but those steps will represent a smaller number of items, and so they won't be such an accurate approximation of the real gradient of the whole data set.
Is there a reason the mean of the loss is calculated over, say, doing the median, since the median is less prone to getting influenced by outliers? In the example you gave, if the third point, which was wrongly predicted, is an outlier, then the derivative would push the function away with an SGD, and a median would be better in that case.
Honestly, I haven't tried using median. The problem with median is it ends up really only caring about one number, which is the number in the middle. So you could end up really pretty much ignoring all of the things in each end. In fact, what it cares about is the order of things.
Yeah, I mean, with the median, you'd have the same issue. Let's say you have a value of 1. Let's say you have 10 values of 1. You have one value of 2, but let's say you have 10 values of 100. So the average would be like around 50 or something, but the median would be 2. So that would be, you'd have the same issue whether you used the mean or the median of your value not appropriately, not being appropriate for your data, but it's just different things would cause that issue.
So my guess is it would end up with something that is only good at predicting one thing in the middle. But I haven't tried it. It would be interesting to see. Well, I guess the other thing that happened with median is you would have 0 gradients, I think, because it's picking the thing in the middle, and you could change your values, the thing in the middle might, well, what is 0 gradients? Bumpy gradients, the thing in the middle would suddenly jump to be a different item. So it might not behave very well. That's my guess. You should try it. Okay, so how do we ask for a few items at a time? It turns out that PyTorch class AI provides something to do that for you. You can pass in any data set to this class called data loader, and it will grab a few items from that data set at a time and ask for how many items for a batch size. And then you can, as you can see, it will grab a few items at a time until it's grabbed all of them. So here I'm saying let's create a collection that contains all the numbers from log 40. Let's pass that into a data loader batch size of 5. And then there's going to be something, it's called an iterator in Python, something that you can ask for one more thing from the iterator. If you pass the iterator to list in Python, it returns all of the things from the iterator. So here are my 3 mini batches. And you'll see here all the numbers from log 40 appear. They appear in random order, and they appear 5 at a time. They appear in random order because shuffle is true. So normally in the training set, we ask for things to be shuffled. So if there's a little bit more randomization, is good. So it makes it harder for it to kind of learn what the data set looks like. So that's how data loader is created. Now, remember though that our data sets actually return tuples, and here I've just got single ints. So let's actually create a tuple. So if we enumerate all the letters in English, then that means that returns 0, A, 1, B, 2, C, etc. That's the data set. So if we pass that to a data loader with a batch size of 6, then as you can see, it returns tuples containing 6 of the first things and the associated 6 of the second things. So this is like our independent variable, and this is like our dependent variable. Okay? And so, and then again, with the batch size won't necessarily exactly divide nicely into the full size of the data set. It might end up in a smaller batch. So basically then we already have a data set, remember? And so we pass it to a data loader, and then we basically say this. An iterator in Python is something that you can actually look through. So when we say for in data loader, it's going to return a tuple. We can destructure it into the first bit and the second bit. And so for the x and y, we can calculate our predictions. We can calculate our loss from the predictions of the packets. We can ask it to calculate our gradients. And then we can update our parameters, just like we did in our toy STD example for quadratic equation. So let's reinitialize our workspace with the same thing like we coded before. Let's create the data loader, this time from our actual MS data set, and create a nice big batch size so we can work each time. And just take a look. Let's just grab the first thing from the data loader. First is a fast AI function, just grab the first thing from an iterator. This is useful.
Okay, I made an offer for something on Craigslist. Oh, okay. Shoot. Okay, yeah, I lowballed them like really a lot. Okay. I guess I should make another offer because I want this thing. Like, I mean, I'm willing to pay the full price for it. The reason I'm lowballing is because, like, he's selling it because he never uses it, and I'm afraid that's going to happen to me. God damn it. I really want this thing though, like so bad. Like I really want this. Alright, replying. Yeah, I mean, the price he's asking for it is fair. I don't know. I just...
We're going to arbitrary mini batch. So here is the shape. We're going to have the first mini batch is 256 rows of 724 models, 28, so 56 flat images, and 256 labels, so one, because it's just the number 0, the 1, and the rest 3 or 7. With the same validation set, so here's the validation data logo. And so let's grab batch here, testing, pass it into, well, why don't we do that? We should, yeah, I guess, yeah, actually for our testing, I'm going to just manually grab the first 4 things just so we can make sure it lines up. So let's grab the first 4 things, we'll call the batch. Pass it into that linear function we created earlier. Remember, linear was just x batch at weights multiplied plus bias. And so that's going to give us 4 results of prediction for each of those 4 images. And so then we can calculate the loss using that loss function we just used. Let's just grab the first 4 items of the training set, and there's the loss. Okay. And so now we can calculate the gradients. And so the gradients are 784 by 1. So in other words, the column where every weight has a gradient. It's what's the change in loss for small change in the parameter. And then the bias has a gradient of a single number, because the bias is just a single number. So we're going to take those 3 steps and put it in a function. So if you pass this calculate gradient, you pass it to x batch and y batch and some model, and it's going to calculate predictions, calculate the loss, and do the backward step. And here we see, calculate gradient, and so we get the, just take a look at the mean of the weights gradient and the bias gradient, and there it is. If I go on the second time, and notice I have not done any step here, it's exactly the same parameters, I get a different value. That's a concern. You would expect to get the same gradient every time you forward with the same data. Why would gradients change? That's because loss.backward does not just calculate the gradients. It calculates gradients and adds them to the existing gradients, the things in the .grad attribute. The reason for that we'll talk later, but the final thing to know is just it does that. So actually what we need to do is to call grad.0 underscore. So .0 returns the tensor containing zeros. And remember underscore does it in place, so that updates the weights.grad attribute in the tensor to contain zeros. So now if I do that, well again, I will get exactly the same number. So here is how you train one epoch with STD. Look through the loader, grabbing the x batch and the y batch, calculate the gradient, prediction, loss, backward. Go through each of the parameters, we're going to be passing those in. So this would be the 768 weights and 1 bias. And then for each of those, update the parameter to go minus equals gradient times 1 reg, that's our gradient descent step, and then 0 reg the next time around. I'm not just saying p minus equals, I'm saying p.data minus equals. And the reason for that is that remember, PyTorch keeps track of all the calculations we do so that we can calculate the gradient. Well, I don't want to calculate the gradient of my gradient descent step. That's like not part of the model, right? So .data is a special attribute in PyTorch where if you write to it, it tells PyTorch not to update the gradients using that calculation. So this is your most basic standard SGD, stochastic gradient descent loop. So now we can answer that earlier question. The difference between stochastic gradient descent and gradient descent is that the gradient descent does not have this here, it loops through each mini batch. The gradient descent does it on the whole data set each time around. So train epoch for gradient descent would simply not have the forward at all, but just calculate the gradient for the whole data set and update the parameters based on the whole data set, which we never do in practice. We always use mini batches with various sizes. Okay, so we can take the function we had before, where we compare predictions to whether we used to compare predictions whether they're greater than 0, right? But now that we're doing the sigmoid, remember the sigmoid will squish everything between 0 and 1. So now we compare the predictions whether they're greater than 0.5 or not. If they're greater than 0.5, just look back at our sigmoid function. So 0, what used to be 0, is now on the sigmoid 0.5. Okay, so we just make that slight change to our measured accuracy. So we calculate the accuracy for some x batch and some y batch. This is actually a set of predictions. Then we take the sigmoid of the predictions, we compare the 0.5 to tell us whether it's true or not. We check what the actual target was to see if one's correct. And then we take the mean of those after the Boolean results. So we can check that accuracy, take that batch, put it through our simple linear model, compare it to the 4 items of the training set, and there's the accuracy. So if we do that for every batch in the validation set, then we can look through the list comprehension of every batch in the validation set, get the accuracy based on some model, stack those all together, so that this is a list, right? But if we would turn that list into a tensor, where the items of the list is the tensor items of the list, that's what stack does. So we can stack up all those.
Kind of looks like it's low accuracy. It's only 0.5.
Take the mean, convert it to a standard Python scalar, like we got Python, round up to 4 decimal places to display, and so here is our validation set accuracy, as we expect. It's about 50%, this is random. So we can now train one epoch. So we can say, remember train epoch needed the parameters. So our parameters in this case are the weights tensor and bias tensor. So train one epoch using the linear 1 model with the linear 1 with these 2 parameters, and then validate. And on that, our accuracy is now 68%. So we've trained an epoch. So let's just repeat that 20 times. Train and validate. And you can see the accuracy goes up and up and up and up to about 90%. So that's all we've built an SGD optimizer, a simple linear function, that is taking about 97% on our simplified MNIST, where this is 3 D7s. So what is that? Let's simplify this through refactoring. So the kind of simple refactoring we're going to do, we're going to do basic idea to create an optimizer parts. The first thing we'll do is we'll get rid of the linear 1 function. So remember the linear one function does x at w plus b. There's actually a class in PyTorch that does that equation for us, so we might as well use it. It's called nn.linear. And nn.linear does two things. It does that function for us, and it also initializes the parameters for us. So we don't have to do weights and bias init parameters anymore. We just create an nn.linear class, and that's going to create a matrix of size 28, 28,1, and the bias of size 1. It will set the bias is true for us. It's already encapsulated in this class, and then when I call that as a function, it's going to do my x at w plus b. So to see the parameters in it, we would expect it to contain 784 weights and 1 bias. We can just call the parameters, and we can destructure it, w comma b, and see, yep, it is 784 and 1 for the weights and bias. So that's cool. So this is just, you could, it could be an interesting exercise for you to create this class yourself from scratch. You should be able to at this point, so that you can confirm that you can recreate something that behaves exactly like nn.linear. So now we've got this object which contains our parameters in a parameters method. We can now create an optimizer. So for our optimizer, we're going to pass it the parameters to optimize and a learning rate. We'll store them away. And we'll have something called step, which goes through each parameter and does that thing we just saw. P.data minus equals p.grad times learning rate. And it's also going to have something called zero grad, which goes through each parameter and zeroes out or we leave it system none. So that's the thing we call basic optimizer. So those are exactly the same line of code we've seen wrapped up into a class. So we can now create an optimizer passing in the parameters of the linear model with these and our learning rate. And so now our training loop is look through each mini batch of data loader, calculate the gradient, opt.step, opt.zeroGrad. That's it. Validation function doesn't change. And so let's put our training loop into a function. It's going to look through a bunch of epochs, call main epoch, print, validate epoch, and run it. And it's the same. I'm getting a slightly different result here. It's much the same idea. Okay. So that's cool, right? We've now refactoring using creating our own optimizer and using fast PyTorch to a linear class. And by the way, we don't actually need to use our own basic optimum. Not surprisingly, PyTorch comes with something just exactly this. And not surprisingly, it's called STD. So, and actually this STD is provided by FastAI. FastAI, PyTorch provides overlapping functionality. They work much the same way. So you can pass to STD, your parameters, and your running rate just like basic optimum. Okay? And train it and get the same result. So as you can see, these classes that are in FastAI PyTorch are not mysterious. They're just pretty, thin wrappers around functionality that we've now written ourselves. So there's a few steps there, and if you haven't done Ready Percent before, then there's a lot of unpacking. So this lesson is kind of the key lesson. It's the one where we just really take a stop and a deep breath at this point and make sure we're comfortable. What's a data set? What's a data loader? What's nn.linear? What's SGT? And if any or all of those don't make sense, go back to where we defined it from scratch using Python code. Well, the data loader will be defined from scratch, but the functionality is not particularly interesting. You can certainly create your own from scratch if you want to. That would be another pretty good exercise. Let's recap some more. FastAI has data loaders class, which is, as we mentioned before, is a tiny class that just you pass a bunch of data loaders and it just stores them away. There's a .train and a .value. Even though it's a tiny class, it's super handy because with that we now have a single object that knows all the data we have, and so it can make sure that your training data loader is shuffled, your validation loader is shuffled, and make sure everything works properly. So that's what the data loaders class is. You can pass in the training validator loader. And then the next thing we have in FastAI is the learner class. And the learner class is something where we're going to pass in our data loaders, we're going to pass in our model, we're going to pass in our optimization function, we're going to pass in our loss function, we're going to pass in our metrics. So all the stuff we've just done manually. That's all learner does, is it's just going to do that for us. So it's just going to call this train model and this train epoch, it's just, it's inside learner. So now if we go learn.fit, you can see again, it's doing the same thing, getting the same result. And it's got some nice functionality, it's picking it up a table for us and showing us the losses and the accuracy and how long it takes. But there's nothing magic, right? You've been able to do exactly the same thing by hand using Python and PyTorch. Okay, so these abstractions are here to let you write this code, save some time, save some cognitive overhead, but they're not doing anything you can't do yourself. And that's important, right? Because if they're doing things you can't do yourself, then you can't customize them, you can't debug them, you can't profile them. So we want to make sure that the stuff we're using is stuff that we understand is good. So this is just a linear function, it's not great. We want a neural network. So how do we turn this into a neural network? Well, remember, this is a linear function, x at w plus d. To turn it into a neural network, we have two linear functions, exactly the same, but with different weights and biases. And in between, this magic line of code, which takes the result of our first linear function and then does a max between that and 0. So a max of reds and 0 is going to take any negative numbers and turn it into zeros. So we're going to do a linear function, we're going to replace the negatives with 0, and then we're going to take that and put it through another linear function. That, believe it or not, is a neural net. So W1 and W2 weight tensors, D1 and D2 bias tensors just like before, so we can initialize them, just like before, and we could now call exactly the same training code we did before to roll these. So res.max 0 is called a rectified linear unit, which you will always see if it was ready. And so here is, and in PyTorch, it already has this function, it's called f.value, and so if we plot it, you can see it's, as we expect, it's 0 for all negative numbers, and then it's y equals x for positive numbers. So, here's the diagram. Rectified linear unit sounds scary, sounds complicated, but it's actually this incredibly tiny line of code, this incredibly simple function. And this happens a lot in deep learning. Things that sound complicated and sophisticated and impressive turn out to be normally super simple, frankly, at least once you know what it is. So why do we do linear layer, value, linear layer? Well, if we got rid of the middle value and just went linear layer, then you could rewrite that as a single linear layer. When you multiply things and add, and then multiply things and add, and you can just change the coefficients and make it into a single multiplying and add. So no matter how many linear layers we stack on top of each other, we can never make anything more kind of effective than a simple linear model. But if you put the non-linearity between linear layers, then actually you have the opposite. This is now where something called the universal approximation theorem holds, which is that if the size of the weight bias matrix is big enough, this can actually approximate any arbitrary function, including the function of how I recognize 3 7s, or whatever. So that's kind of amazing, right? This tiny thing is actually a universal function approximator. As long as you have W1, D1, W2, and D2 have the right numbers. And they don't have the right numbers, you use STD. It could take a lot of time, it could take a lot of memory, but the basic idea is that there is some solution to any computable problem. And this is one of the biggest challenges.
Oh no, I got an offer. See, I was lowballing him because, like, you know, he's selling it because he never uses it and it just takes up space in his apartment. So, like, I don't know if I want to pay to have something I'll never use and it'll just take up in my apartment. Like, I thought he was working, I thought he was doing a pretty good offer already, but, like, but he's accepting my, one of my offers. Oh man. And it's a damn good offer. I mean, he yeah, I mean, I was thinking about buying one of these without frickin' you know, checking Craigslist or anything. So, like, you know, if I wanted to buy this product straight up, like, you know, I would have to pay double what I'm gonna pay here. But, you know, as I said, I'm a little bit hesitant to pay anything for this because I just don't know if I'm gonna use it, and most people don't use it. But at the same time, I really want this. I really wanted to try it, and you know, without buying it from him, it's gonna cost me maybe perhaps double. Like, once all shipping and all that is in place, it'll definitely cost me double. So I can get it for like half price. Okay, sold. Okay, sold. I can bring you a check. Use Google Pay. Can I pick it up today? Yeah, I'm gonna buy this thing. Okay, but it's gonna be like a 100-pound pain in the ass to, like, bring in here. It's gonna be big. It's gonna take up space. Like, but yeah, I've been wanting to try it. I'm gonna get it for half price. Send. God damn it.
A lot of beginners have to DeepMind is that there's nothing else to it. Like, there's often this, like, okay, how do I make a neural net? Oh, that is a neural net. Or how do I do deep learning training? Where there's DD, there's things to, like, make training faster, there's, you know, things to need few less parameters, but everything here is just performance tweaks, honestly. Right? So this is, you know, this is the key understanding of training a neural network. Okay, we can simplify things a bit more. We already know that we can use nn.linear to replace the weight bias, so let's do that for both of the linear layers. And then since we're simply taking the result of one function passing into the next, and take the result of that function, pass to the next, and so forth, and then return to n, this is called function composition. Function composition is when you just take the result of one function, pass to a new one, take the result of one function, pass to a new one. And so every pretty much neural network is just doing function composition of linear layers, and these are called activation functions, or non-linear layers. So PyTorch provides something to do function composition for us, and it's called nn.sequential. So it's going to do a linear layer, pass the result to a w, pass the result to a linear layer. You'll see here I'm using f.w, I'm using nn.w. This is identical, which is exactly the same thing. This is a class rather than a function. Yes, Rachel?
By using the non-linearity, while using a function that makes all negative output zero, we can give the gradients in that zero and stop the learning process due to many zero gradients.
Well, that's a fantastic question. And the answer is yes, it does. But there won't be zero for every image. And remember, mini dashes are shuffled. So even if it's zero for every image in one mini dash, it won't be the next mini dash, it won't be the next time around go for another epoch. So yes, it can get zeros. And if the neural net ends up with a set of parameters such that lots and lots of inputs end up as zeros, you can end up with whole mini batches of zero. And you can end up in a situation where some of the neurons remain inactive at zero. They're basically dead units. And this is a huge problem. It basically means you're wasting computation. So there's a few tricks to avoid that, which we'll be learning about a lot. Now, one simple trick is to not make this thing flat here, but just make it a less thick line. That's why leaky rectified unit. And there you have it. As we'll learn, though, even better is to make sure that we just kind of initialize to sensible initial values, not too big, not too small, and step by sensible amounts that are particularly not too big. And generally, if we do that, we can keep things in the zone where they're positive most of the time. But we are going to learn about how to actually analyze inside the network and find out how many dead units we have, how many of these zeros we have, because as I point out, they are bad units, they don't do any work. And they'll continue not to work if enough of the inputs end up in zero. Okay, so now that we've got a neural net, we can use exactly the same one we had before. This time we pass in the simple net instead of the linear one. Everything else is the same. And we can call fit, just like before. And generally, as your models get deeper, so here we've gone from one layer to, and I'm only counting the parameter layers. Of course, there's three. I always got two. There's two trainable layers. So I've gone from 1 layer to 2. I've dropped my learning rate from 1 to 0.1 because the deeper models, it'll tend to be kind of bumpier, less nice to behave, so often you need to use lower learning rates. And so we're training for a while, okay? And we can actually find out what that training looks like by looking inside our learner, and there's an attribute we create for you called recorder, and that's going to record everything that appears in this table, basically.
Okay, we're at an hour, so I don't want to. I don't want to what. Let me put it this way. I want to take a break. I'll come back as soon as I can. All right. All right, welcome back. We're going to try to get through more of this video. I'm going to be eating tortillas while I'm watching it, though.
Well, these things, the training loss, the validation loss, and the accuracy, or any metrics. So recorded values contains that kind of table of results. And so item number 2 of each row will be the accuracy. And so the capital L class, which I'm using here, has a nice little method called item plot that will get the second item from every row, and then I can plot that to see how the training went, and I can get the final accuracy like so, by grabbing the last row of the table, grabbing the second, index 2, 0.2, and my final accuracy, not bad, 98.3%. So this is pretty amazing. We now have a function that can solve any problem to any level of accuracy if we can find the parameters. And we have a way to find, hopefully the best, or at least a very good set of parameters for any function. So this is kind of magic. Yes, Rachel?
How could we use what we're learning here to get an idea of what the network is learning along the way, like Zyber and Fergus did, more or less?
We'll look at that later. Not in the full detail of the paper. But basically, you can look in the dot parameters to see the values of those parameters. And at this point, well, I mean, what did you try to solve, right? You've actually got now the parameters. So if you want to grab the model, you can actually see learn.model. So we can look inside learn.model to see the actual model that we just trained. And you can see it's got the 3 things, the linear, the nonlinear. And what I kind of like to do is put that into a variable, make it easy to work with. And you can grab one layer by indexing. You can look at the parameters. And that just gives you something called a generator, something that will give me a list of parameters when I ask for them. I can just go weight bias equals to destructure them. And so the weight is 30 by 784 because that's what I asked for. So one of the things to note here is that to create a neural net, so from one layer, I actually have 30 apples, not just one, right? So I'm kind of generating lots of units, generating lots of features. So it's kind of like 30 different linear models here. And then I combine those 30 back into one. So you could look at one of those by having a look at here. So there's the numbers in the first row. We could reshape that into the original shape of the images. And put it into a model. And there it is, right? So you can see this is something, so it's cool, right? We can actually see here we've got something which is kind of learning to find things at the top and the bottom and the middle. And so we can look at the second one. Okay, no idea what that's showing. And so some of them are kind of, I've probably got far more than I need, which is why they're not that obvious. But you can see, yeah, here's another thing that's pretty similar. Here's something kind of looking for this little bit in the middle. So yeah, this is the basic idea. To understand the features that are not the first layer, but later layers, you have to be a bit more sophisticated. But yeah, this is the first layer ones, you can just plot them. Okay, so then, just to compare, we could use the full FastAI toolkit, so grab our data loaders by using data loaders from folder, as we've done before, create a CNN learner and a ResNet, and fit it for a single epoch, and whoa, 99.7, right? So we did 40 epochs and got 98.3. As I said, using all the tricks, you can really speed things up and make things a lot better. And so by the end of this course, or at least both parts of this course, you'll be able to, from scratch, get this 99.7 in a single epoch. All right, so jargon. So jargon just reminds us, value, functions return 0 for negatives, mini batch, a few inputs and labels, which optionally are randomly selected, The forward pass is where we calculate the predictions. The loss is the function that we're going to take the derivative of, and then the gradient is the derivative of the loss with respect to each parameter. The backward pass is when we calculate those gradients. Gradient descent is that full thing of taking a step in the direction opposite to the gradients after calculating the loss, and then the learning rate is the size of the step that we take. Other things to know, perhaps the two most important pieces of jargon are all of the numbers that are in a neural network. The numbers that we're learning are called parameters, and then the numbers that we're calculating, so every value that's calculated, every matrix multiplication element that's calculated, they're called activations. So activations and parameters are all of the numbers in the neural net, and so be very careful when I say from here on in these lessons activations or parameters, you've got to make sure you know what those mean, because that's the entire, basically, almost the entire set of numbers that exist inside the neural net. So activations are calculated, parameters are learned. We're doing this stuff with tensors, and tensors are just regularly checked arrays. Rank 0 tensors we call scalars, rank 1 tensors we call vectors, rank 2 tensors we call matrices, and continue on to rank 3 tensors, rank 4 tensors, and so forth. And rank 5 tensors are very common in deep learning, so don't be scared going up to higher numbers of dimensions. Okay, so let's have a break. Oh, we've got a question. Okay.
Is there a rule of thumb for what nonlinearity to choose, given that there are many?
Yeah, there are many non-linearities to choose from, and it doesn't generally matter very much to choose. So let's choose value, or Vicky value, or yeah, whatever. Anyone should work fine. Later on, we'll look at the minor differences between them, but it's not so much something that you pick on a per problem. It's more like some take a little bit longer, a little bit more accurate, some a bit faster, and a little bit less accurate. That's a good question. Okay, so before you move on, it's really important that you finish the questionnaire for this chapter, because there's a whole lot of concepts that we've just done. So, try to go through the questionnaire, go back and relook at the notebook, and please run the code, do the experiments, and make sure it makes sense. All right, let's have a 7-minute break. See you back here in 7 minutes' time. Okay, welcome back. So, now that we know how to create a training neural net, let's cycle back and look deeper at some applications. And so we're going to try to kind of interpolate in. From one end, we've done the kind of from scratch version. At the other end, we've done the kind of...
Okay, so I don't think I ran the code. So I'm going to do that. Yeah, I think I just ran the code from the last lesson. But this is going to be... yeah. I'm not sure if I ran all the code. I mean, we could just go and run it. I mean, it's just running the code doesn't, I think, really... Let's see here. What was he talking about? He was talking about... I mean, I've run this before. Let's just run the code. I mean, making sure I 100%. Oh, you know what I wanted to do? I wanted to change this to be analyzing digits 6 and 9 instead of 7 and 3. But unfortunately it looks like this MNIST sample doesn't contain all of them. So let's do a help on or let's do a help on URLs. Okay, and then rerun the cell. Okay, so now, yep, so we can see we've got all the different kind of, what the hell? All the different kind of, really? I think that might be worth a Discord. Yeah, that's definitely worth a Discord post. Okay. What is this? Okay, so now I can, yep, perfect. Okay, so we've got, yep, we've got everything good to go. Let's see if we can use a different URL. So here, yep, here we've got a sample, but let's just pull the whole thing instead of just the sample. Okay, and then we'll see if we can get um, the digits 6 and 9. Oops, so, oh wait. Ah, God damn it. Okay, well, we can't, I don't know how to get the digits 6 and 9. I think I would need a different data set, because right now we're using this MNST sample. Uh, yeah, so let's go to this URL. Yeah. But this is part of the FastAI files. Okay, so let's do MNIST. Yeah. And let's see if we can just download this. Yeah, here it is. Ah. Now, you know what? This is going to be too much trouble. Let's just run the code as is and then move on. Now, this code I did run before. Now, why is the output disappearing, but not? Oh, I see. Okay, it was still thinking. It looks like if you run a cell before the previous cell had completed, you're not running the cell. You're just saying this cell is now allowed to run as long as the previous cell is finished running. Because I always wondered about that, like, oh, what if you run a bunch of cells and the first cell takes uh, longer to run, takes a long time to run, and you didn't wait to click the next cell? What happens? Oh, well, the next cell just goes in queue and then runs after the first cell finishes. My stomach hurts. Yeah, I don't know what any of this code does. We got the weight, we got the bias, we got the train. Like, I figured out the last lesson, like the lesson where I had to make my own project, like, made a lot of sense to me. I'm more of a like like the theory and stuff is, I think, like let's put it this way, like I was the only person who was able to get Binder to work, but I doubt I'll be the first person to understand any of these technical concepts. I'll probably be the last person to figure these out. Who knows? I mean, it's always important to be charitable towards yourself and towards others. You don't want to sell yourself short or miss out on opportunities because you didn't think you were good enough for them. But then it turns out not only were you good enough for them, you were the only person who could make a difference, and you just didn't do it because you have basically dysmorphia over your own abilities. Okay, so yeah, it looks like all the code is going just fine. We've got learn.fit one cycle, so we're getting our model. Could probably do an export statement after this to get the export.pickle file. So that's going to take a while to run. Let's go back and keep watching the video.
Kind of 4 lines of code version. And we're going to gradually nibble at each end until we find ourselves in the middle, and we've touched on all of it. So let's go back to the kind of 4 lines of code version and delve a little deeper. So let's go back to pets. And let's think though about like how you actually start with a new data set and figure out how to use it. So the data set we provide is easy enough to untar. You just say untar, download it, untar it. If it's a data set that you're getting, you can just use the terminal or Hyper or Python or whatever. So let's assume we have a path that's pointing at something. So initially you don't know what that something is. So we can start by doing else to have a look and see what's inside there. So the pets data set that we saw in lesson 1 contains 3 things: annotations, images, and models. And you'll see we have this little trick here where we say path.base path equals, and then the path to our data. And that just does a little simple thing where when we print it out, it just doesn't show us, it just shows us relative to this path. It's a bit convenient. So if you go and have a look at the README for the original pets dataset, it tells you what these images and annotations folders are, and not surprisingly, the images path, if we go path/images, that's how we use path to grab a subdirectory, and then ls, we can see here are the names, the paths to the images. As I mentioned here, most functions and methods in FastAI return a collection, don't return a Python list, but they return a capital L. And a capital L, as we briefly mentioned, is basically an enhanced list. One of the enhancements is the way it prints. The representation of it starts by showing you how many items there are in the list, in the collection. So there's 7,394 images. And if there's more than 10 things, it truncates it, just to avoid filling up the screen. So there's a couple of little conveniences there. And so we can see from this output that the file name, as we mentioned in lesson 1, if the first letter is capital, it means it's a cat. And if the first letter is lowercase, it means it's a dog. But this time we're going to do something more complex, or a lot more complex, which is figure out what breed it is. And so you can see the breed is kind of everything up to, in the file name, it's everything up to the last underscore before this number is the breed. So we want to label everything with its breed, so we're going to take advantage of this structure. So the way I would do this is to use a retro expression. A retro expression is something that looks at a string and basically lets you kind of pull it apart into its pieces in very flexible ways. It's kind of simple little language for doing that. If you haven't used retro expressions before, please Google retro expression tutorial now and look. It's going to be like one of the most useful tools you'll come across in your life. I use them almost every day. I won't go into details about how to use them. There's so many great tutorials, and there's also a lot of great exercises. There's regex is short for retro expression. There's regex crosswords. There's regex Q&A. There's all kinds of cool regex things. A lot of people like me love this tool. In order to
There's also a regex lesson in the FastAI NLP course, maybe even 2 regex lessons.
Oh yeah, I'm sorry for forgetting about the FastAI NLP. What an excellent resource that is. So retro expressions are a bit hard to get right the first time. So the best thing to do is to get a sample string. So to good way to do that would be to just grab one of the file names, so let's pop it in FN, and then you can experiment with retro expressions. So RE is the retro expression module in Python, and find all will just grab all the parts of the retro expression that have parentheses around them. So this retro expression, and R is a special kind of string in Python, which basically says don't treat backslash as special, because normally in Python like backslash n means a new line. So here's a string which I'm going to capture any letter 1 or more times, followed by an underscore, followed by a digit 1 or more times, followed by anything, I probably just use backslash dot, that's fine, followed by the letters JPG, followed by the end of the string. And so if I call that retro expression against my file name's name, oh, looks good, right? So we can check it out. So now that seems to work, we can create a data block where the independent variables are images, independent variables are categories. Just like before, get items is going to be get image files. We're going to split it randomly as per usual. And then we're going to get the label by calling regex labeler, which is just a handy little FastAI class which labels things with a retro expression. We can't call the retro expression, this particular retro expression, directly on the path object. We actually want to call it on the name attribute. And FastAI has a nice little function called using attribute, which takes this function and changes it to a function which will be passed to this attribute. But it's going to be using regex labeler on the name attribute. And then from the data block, we can create the data loaders as usual. There's two interesting lines here, resize and org transforms. Org transforms we have seen before in Notebook 2, in the section called data augmentation. And so org transforms was the thing which can zoom in and zoom out and warp and rotate and change contrast and change brightness and so forth, and to kind of give us, almost like giving us more data being generated synthetically from the data we already have. And we also learned about random resize crop, which is a kind of a really cool way of getting, ensuring you get square images at the same time that you're augmenting the data. Here, we have a resize to a really large image, like, by deep learning standards, 460 by 460 is a really large image. And then we're using org transforms with a size, so that's actually going to use random resize crop to a smaller size. Why are we doing that? This particular combination of two steps does something which I think is unique to FastAI, which we call presizing. And this way is, I will show you this beautiful example of PowerPoint wizardry that I'm so excited about to show how presizing works. What presizing does is that first step, where we say resize to 460 by 460, is it grabs a square, and it grabs it randomly. If it's a kind of landscape orientation photo, it'll grab it randomly, sort of take the whole height and randomly grab somewhere from along the side. If it's a portrait orientation, then it'll grab it, take the full width and grab a random bit from top to bottom. So I'm going to take this area here, and here it is, right? And so that's what the first resize does. And then the second org transforms bit will grab a random warped crop, possibly rotated, from in here, and will turn that into a square. And so it does, so there's two steps. It's first of all resize to a square that's big, and then the second step is do a kind of rotation and warping and zooming stage to something smaller, in this case 224 by 224. Because this first step creates something square, and always is the same size, the second step can happen on the GPU. And because normally things like rotating and image warping actually pretty slow. Also, normally doing a zoom and a rotate and a warp actually is really disruptive to the image, because each one of those things requires an interpolation step, which it's not just slow, it actually makes the image really quite low quality. So we do it in a very special way in FastAI, I think it's unique, where we do all of these kind of coordinate transforms, like rotations and warps and zooms and so forth, not on the actual pixels, but instead we kind of keep track of the changing coordinate values in a non-lossy way, so the full floating point value. And then once at the very end, we then do the interpolation. There's also quite striking. Here is what the difference looks like. Hopefully you can see this on the video. On the left is our presizing approach, and on the right is the standard approach that other libraries use. And you can see that the one on the right is a lot less nicely focused, and it also has like weird things, like this should be grass here, it's actually got its kind of bum sticking way out. This has a little bit of weird distortions, this has got loads of weird distortions. So you can see the presized version really ends up way, way better. And I think we have a question, Rachel.
Are the blocks in the data block ordered list? Do they specify the input and output structures respectively? Are there always two blocks, or can there be more than two? For example, if you wanted a segmentation model, would the second block be something about segmentation?
So yeah, this is an ordered list. So the first item says I want to create an image, and then the second item says I want to create a category. So it's my independent and dependent variable. You can have one thing here, you can have three things here, you can have any amount of things here you want. Obviously, the vast majority of the time will be two. Only there's independent variable and dependent variable. We'll be seeing this in more detail later, although if you go back to the earlier lesson when we introduced data blocks, I do have a picture kind of showing how these pieces fit together. So after you put together your data block, create your data loaders, you want to make sure it's working correctly. So the obvious thing to do for a computer vision data block is show batch. And show batch will show you the items, and you can just make sure they look sensible, it looks like the labels are reasonable. If you add unique equals true, then it's going to show you the same image with all the different augmentations. This is going to make sure your augmentations work. If you make a mistake in your data block, for this example, there's no resize, so the different images are going to be different sizes, so it will be impossible to collate them into a batch. So if you call .summary, this is a really neat thing, which will go through and tell you everything that's happening. So I collect any items, how many did I find, what happened when I split them, what are the different variables, independent variables I'm creating, let's try and create one of these. Here's each step, create my image, create categorize, here's what the first thing gave me, an American Bulldog. Here's the final sample, is this image, this size, this category, and then eventually it says, uh-oh, it's not possible to collect your items. I tried to collect the zero index members of your tuples, in other words, that's the independent variable, and I got, this was size 500 by 375, this was 375 by 500. Oh, I can't collect these into a tensor because they're different sizes. So this is a super great debugging tool for debugging your data blocks.
I have a question. How does the item transforms presize work if the resize is smaller than the image? Is a whole width or height still taken, or is it just a random crop with a size value?
So if you remember back to lesson 2, we looked at the different ways of creating these things. You can use squish, you can use pad, or you can use crop. So if your image is smaller than the precise value, then squish will really be zoom. So it will just small stretch, it'll stretch it. And then pad and crop will do much the same thing. And so you'll just end up with the same. This looks like these, but it'll be a kind of lower, more pixelated resolution. It's going to zoom in a little bit. Okay, so a lot of people say that you should do a hell of a lot of data training before you model. We don't. We say model as soon as you can. Because remember what we found in Notebook 2, your model can teach you about the problems in your data. So as soon as I got to a point where I have a data block that's working and I have data loaders, I'm going to do a model. And so here, it also tells me how I'm going. So I'm getting 7% error. Wow, that's actually really good for a PETS model. And so at this point, now that I have a model, I can do that stuff we learned about earlier in O2, Notebook 2, where we train a model and use it to clean the data. So we can look at classification, the confusion matrix, top losses, the image cleaner widget, so forth. Okay. Now, one thing interesting here is in Notebook 4, we included a loss function when we created a learner, and here we don't ask for a loss function. Why is that?
kind of looking out the window, you can probably see there's a bunch of people there. Oh, they're probably having a party or something. But I've just never seen so many people aggregated out in that area before, and it's not like it's like like they're just in the middle of the they're in kind of a weird area to aggregate to. So there's just a bunch of people standing in like kind of an unusual area to stand. Is why I'm staring out my window.
That's because first AI will try to automatically pick a somewhat sensible loss function for you. And so for an image classification task, it knows what loss function is the normal one to pick. It's done for you. But let's have a look and see what it actually did pick. So we can have a look at learn.lossfunc, and we'll see it is cross-entry loss. What on earth is cross-entry loss? I'm glad you asked. Let's find out. Cross-entry loss is really much the same as the MNIST loss we created with that sigmoid and the 1 minus predictions and predictions. But it's a kind of extended version of that. And the extended version of that is that torch.where that we looked at in notebook 4 only works when you have a binary outcome. In that case, it was is it a 3 or not. But in this case, we've got which of the 37 pet breeds is it. So we want to kind of create something just like that sigmoid and torch.where, but which also works nicely for more than 2 categories. So let's see how we can do that. So first of all, let's grab a batch. Yes.
Why do you want to build a model before cleaning the data? I would think a clean data set would help in training.
Yeah, absolutely. A clean data set helps in training. But remember, as we saw in notebook 2, an initial model helps you clean the data set. So remember how plot losses help us identify mislabeled images. And the confusion matrix helps us recognize which things we were getting confused and might need fixing. And the image classifier cleaner actually let us find things like an image that contained 2 layers rather than 1 layer and clean it up. So a model is just a fantastic way to help you zoom in on the data that matters, which things seem to have the problems, which things are most important, stuff like that. So you go through and you clean it with the model helping you, and then you go back and train it again with the clean data. Thanks for the question.
Oh, I see.
Okay, so in order to understand cross-entry loss, let's grab a batch of data, which we can use.
Yeah, that was a good question. Why are you cleaning up the data after it's already been trained? Wouldn't you want to have the data cleaned up before you train it? But the answer is we're actually training it twice. We're going to train it once, and we're going to see what went wrong, we're going to clean it up, and then we're going to train it again.
Just DLs.one batch. And that's going to grab a batch from the training set. We could also go first, DLs.train, and that's going to do exactly the same thing. And so then we can destructure that into the independent variable. And so the dependent variable shows us, we've got a batch size of 64, but shows us the 64 categories. And remember, those numbers simply refer to the index of the vocab. So for example, 16 is a boxer. And so that happens automatically when we say show batch, it shows us those strings. So here's a first mini batch. And so now we can do the predictions. That is the activations of the final layer of the network by calling it preds. And you can pass in a data loader. And data loader can really be anything that's going to return a sequence of mini batches. So we can pass in a list containing a mini batch as a data loader. And so that's going to get the predictions for 1 mini batch. So here's some predictions. Okay, so the actual predictions, if we go preds 0.sum to grab the predictions for the first image and add them all up, they add up to 1. And there are 37 of them. So that makes sense, right? It's like the very first thing is what is the probability that that is a else vocab. So the first thing is what's the probability it's an Abyssinian cat. It's 10 to the negative 6, you see, and so forth. So it's basically like it's not this, not this, not this, and you can look through and oh, here, this one here, let's see what it is. So,
all right, we're at the 1.5 mark. I'm gonna take a quick break, come back, and hopefully we'll finish out this whole video. Then I'll go and answer the questions, run the code, and I think that'll be it. It's kind of a shorter lesson this week. All right, we've got a red circle again with a clicking clock, so let's keep going.
How did it, so we obviously want the probabilities to sum to 1 because it would be pretty weird if they didn't. It would say, the probability of being one of these things is more than 1 or less than 1, which would be extremely odd. So how do we go about creating these predictions where each one is between 0 and 1, and they all add up to 1? To do that, we use something called softmax. Softmax is basically an extension of sigmoid to handle more than 2 levels, 2 categories. So remember the sigmoid function looked like this. And we use that for our 3s versus 7s model. So what if we want 37 categories rather than 2 categories? We need 1 activation for every category. So actually, the 3s and 7s model, rather than thinking of that as an is3 model, we can actually say, oh, that has 2 categories. So let's actually create 2 activations, one representing how 3 like something is, and one representing how 7 like something is. So let's say, let's just say that we have 6 MS digits, and these were the, and this first column were the activations of my model for one activation, and the second column is for a second activation. So my final layer actually has two activations now. So this is like how much like a 3 is it, and this is how much like a 7 is it. So this one is not at all like a 3, and it's slightly not like a 7. This is very much like a 3 and not much like a 7, and so forth. So we can take that model and rather than having one activation for like is 3, we can have two activations for how much like a 3, how much like a 7. So if we take the sigmoid of that, we get two numbers between 0 and 1, but they don't add up to 1. So that doesn't make any sense. It can't be 0.66 chances to 3 and 0.56 chances to 7, because every digit in that data set is only one or the other. So that's not going to work. But what we could do is we could take the difference between this value and this value and say that's how likely it is to be a 3. So in other words, this one here with a high number here and a low number here is very likely to be a 3. So we can basically say in the binary case, these activations, what really matters is their relative confidence of being a 3 versus a 7. So we can calculate the difference between column 1 and column 2, column index 0 and column index 1. Right? And here's the difference between the two columns. There's that big difference. And we can take the sigmoid of that. Right? And so this is now giving us a single number between 0 and 1. And so then, since we've got two columns, we could make column index 0 the sigmoid, and column index 1 could be 1 minus that. And now, look, these all add up to 1. So here's probably a 3, probably a 7. For the second one, probably a 3, probably a 7, and so forth. So, like, that's a way that we could go from having two activations for every image to creating two probabilities, each of which is between 0 and 1, and each pair of which adds to 1. Great. How do we extend that to more than two columns? To extend it to more than two columns, we use this function, which is called softmax. So softmax is equal to e to the x divided by sum of e to the x. Just to show you, if I go softmax on my activations, I get 0.6025, 0.3975, 0.6025, 0.3975, I get exactly the same thing. Right? So softmax in the binary case is identical to the sigmoid that we just looked at. But in the multi-category case, we basically end up something like this. Let's say we're doing teddy bear, grizzly bear, brown bear. And for that, remember our neural net is going to have the final layer will have three activations. So let's say it was 0.02, negative 2.49, 1.25. But to calculate softmax, I first go e to the power of each of these three things. So here's e to the power of 0.02, e to the power of negative 2.49, e to the power of 3.4, e to the power of 1.25. Okay. Then I add them up. So there's a sum of the x's. And then softmax will simply be 1.02 divided by 4.6. And then this one will be 0.08 divided by 4.6, and this one will be 3.49 divided by 4.6. So since each one of these represents each number divided by the sum, that means that the total is 1. Okay? And because all of these are positive, and each one is an item divided by the sum, it means all of these must be between 0 and 1. So this shows you that softmax always gives you numbers between 0 and 1, and they always add up to 1. So to do that in practice, you can just call torch.softmax, and it will give you this result of this function. So you should experiment with this in your own time. Write this out by hand, and try putting in these numbers, right, and see how you get back the numbers you're going to get back. Make sure this makes sense to you. So one of the interesting points about softmax is, remember I told you that x is e to the power of something. And what that means is that e to the power of something grows very, very fast, right? So like x to 4 is 54, x of 8 is 23,980, right? It grows super fast. And what that means is that if you have one activation that's just a bit bigger than the others, its softmax will be a lot bigger than the others. So intuitively, the softmax function really wants to pick one class among the others, which is generally what you want, right? When you're trying to train a classifier to say which breed is it, you kind of want it to pick one and kind of go for it, right? And so that's what softmax does. That's not what you always want. So sometimes at inference time, you want to be a bit cautious. So you kind of got to remember that softmax is always the perfect approach. But it's a default, it's what we use most of the time, and it works well in a lot of situations. So that is softmax. Now, in the binary case for the MNIST 3 versus 7s, this was how we calculated MNIST loss. We took the sigmoid, and then we did either 1 minus that or that as our loss function. Which is fine, as you saw it, it worked, right? And so we could do this exactly the same thing. We can't use torch.where anymore because targets aren't just 0 or 1, targets could be any number from 0 to 36. So we could do that by replacing the torch.where with indexing. So here's an example for the binary case. Let's say these are our targets, 0, 1, 0, 1, 1, 0. And these are our softmax activations, which we calculated before. Those are some random numbers just for example. So one way to do, instead of doing torch.where, we could instead, look at this. I could say, I could grab all the numbers from 0 to 5, and if I index into here with all the numbers from 0 to 5, and then my targets, 0, 1, 0, 1, 0, 1, 0, then what that's going to do is it's going to pick, for row 0, it'll pick 0.6. And then for row 1, it'll pick 1, 0.49. For row 2, it'll pick 0.13. For row 4, it'll pick 1, 0.03, and so forth. So this is a super nifty indexing expression, which you should definitely play with, right? And it's basically this trick of passing multiple things to the PyTorch indexer. The first thing says, which rows should you return? And the second thing says, each of those rows, which column should you return? So this is returning all the rows and these columns for each one. And so this is actually identical to torch.where. So isn't that tricky? And so the nice thing is, we can now use that for more than just two values. And so here's the fully worked out thing. So I've got my 3's column, I've got my 7's column, here's that target, here's indexes from 0, 1, 2, 3, 4, 5. And so here's 0, 0, 0.6, 1, 1, 0.49, 0, 2, 0.13, and so forth. So yeah, this works just as well with more than two columns. So we can add, for doing a full MNIST, so all the digits from 0 to 9, we could have 10 columns, and we would just be indexing into 10. So this thing we're doing, where we're going minus our activations matrix, all the numbers from 0 to n, and then our targets. is exactly the same as something that already exists in PyTorch called f.nll-loss, as you can see, exactly the same. Right, so again, we're kind of seeing that these things inside PyTorch and FastAI are just little shortcuts and stuff we can write ourselves. NLL-loss stands for negative log likelihood. Again, it sounds complex, but actually it's just this index expression. Rather confusingly, there's no log in it. We'll see why in a moment. So let's talk about logs. So this loss function works quite well, as we saw in Notebook 04. It's basically just, it is exactly the same as we saw in Notebook 04, just a different way of expressing it. But we can actually make it better. Because remember, the probabilities we're looking at are between 0 and 1. So they can't be smaller than 0, they can't be greater than 1. Which means that if our model is trying to decide whether to predict 0.99 or 0.999, it's going to think that those numbers are very, very close together, but won't really care. But actually, if you think about the error, if there's like 1,000 things, then this would like be 10 things are wrong, and this would be like 1 thing is wrong. But this is really like 10 times better than this. So really what we'd like to do is transform the numbers between 0 and 1 to instead be between negative infinity and infinity. And there's a function that does exactly that, which is called logarithm. Okay, so the numbers we can have can be between 0 and 1. And as we get closer and closer to 0, it goes down to infinity, and then at 1, it's going to be 0. And we can't go above 0 because our loss function, we want to be negative. So this logarithm, in case you forgot, hopefully you vaguely remember what logarithm is from high school, but basically the definition is this. If you have some number that is y that is b to the power of a, then logarithm is defined such that a equals the logarithm of y comma b. In other words, it tells you b to the power of what equals y. Which is not that interesting in itself, but one of the really interesting things about logarithms is this very cool relationship, which is that log of a times b equals log of a plus log of b. And we use that all the time in deep learning and machine learning because this number here, a times b, can get very, very big or very, very small if you multiply things. A lot of small things together, you get a tiny number. If you multiply a lot of big things together, you get a huge number. It can get so big or so small that the kind of precision in your computer's floating point gets really bad. Whereas this thing here, adding, is not going to get out of control. So we really love using logarithms, like particularly in a deep neural net where there's lots of layers. We're kind of multiplying and adding many times, so this kind of tends to come out quite nicely. So when we take the probabilities that we saw before, the things that came out of this function, and we take their logs, and we take the mean, that is called negative log likelihood. And so this ends up being kind of a really nicely behaved number because of this property of the log that we described. So if you take the softmax, and then take the log, and then pass that to an NLL-loss, because remember I didn't actually take the log at all, despite the name, that gets you gross entropy loss. So that leaves an obvious question of why doesn't the NLL-loss actually take the log? And the reason for that is that it's more convenient computationally to actually take the log back at the softmax step. So PyTorch has a function called log softmax. And so since it's actually easier to do the log at the softmax stage, it's just faster and more accurate, PyTorch assumes that you use soft log max and then pass that to NLL-loss. So NLL-loss does not do the log, it assumes that you've done the log beforehand. So log softmax followed by NLL-loss is the definition of cross entropy loss in PyTorch. So that's our loss function. And so you can pass that to activations and some targets and get back a number. And pretty much everything in PyTorch, every one of these kinds of functions, you can either use the NN version as a class, like this, and then call that object as a function, or you can just use f dot with the camel case name as a function directly. And as you can see, they're exactly the same number. People normally use the class version. In the documentation in PyTorch, you'll see it normally uses the class version, so we're going to use the class version as well. You'll see that it's returning a single number, and that's because it takes the mean, because a loss needs to be, as we discussed, the mean. But if you want to see the underlying numbers before taking the mean, you can just pass in reduction equals none, and that shows you the individual cross entropy losses before taking the mean. Okay. Great. So this is a good place to start with our discussion of loss functions and such things. Rachel, were there any questions about this?
Why does the loss function need to be negative?
Well, I mean, I guess it doesn't, but it's we want something that the lower it is, the better. And we kind of need it to cut off somewhere. I have to think about this more during the week because it's a bit tired. Yeah, so let me refresh my memory when I'm awake. Okay, now next week, well, not for the video. Next week actually happened last week, so the thing I'm about to say is actually weird. So next week we're going to be talking about data ethics, and I wanted to kind of segue into that by talking about how my week's going, because a week or two ago I did a.
So ethics, this is like the more interesting chapter to me. I'm going to play this at normal speed.
As part of a lesson, I actually talked about the efficacy of masks, and specifically wearing masks in public. And I pointed out that the efficacy of masks seemed like it could be really high, and maybe everybody should be wearing them. And somehow I found myself as the face of a global advocacy campaign. And so if you go to masksforall.co, you will find a website talking about masks. And I've been on, TV shows in South Africa and the US and England and Australia and on radio and blah, 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 talking about masks. Why is this? Well, it's because as a data scientist, I noticed that the data around masks seemed to be getting misunderstood. And it seemed that misunderstanding was costing possibly hundreds of thousands of lives. Literally in the places that were using masks, it seemed to be associated with, orders of magnitude fewer deaths. And one of the things we'll talk about next week is what's your role as a data scientist? I strongly believe that it's to understand the data and then do something about it. And so nobody was talking about this. So I ended up writing an article that appeared in the Washington Post that basically called on people to really consider wearing masks, which is this article. I was lucky. I managed to kind of get a huge team of brilliant, not huge, a pretty decent-sized team of brilliant volunteers who helped, kind of build this website and some PR folks and stuff like that. But what became clear was, I was talking to politicians, senators, staffers, and what was becoming clear is that people weren't convinced by the science, which is fair enough, because it's hard to, when the WHO and the CDC is saying you don't need to wear a mask, and some random data scientist is saying that doesn't seem to be what the data is showing, you've got half a brain, you would pick the WHO and the CDC, not the random data scientist. So I really felt like if I was going to be an effective advocate, I needed to sort the science out. And credentialism is strong. And so it wouldn't be enough for me to say it. I needed to find other people to say it. So I put together a team of 19 scientists, including, a professor of sociology, a professor of aerosol dynamics, the founder of an African movement that kind of studied preventative methods for tuberculosis, a Stanford professor who studies mask disposal and cleaning methods, a bunch of Chinese scientists who study epidemiology modeling, a UCLA professor who is one of the top infectious disease epidemiologist experts, and so forth. So this kind of all-star team of people from all around the world. And I had never met any of these people before. So, well, no, not quite true. I knew Austin a little bit, and I knew Zeynep a little bit. I knew Lex a little bit. But on the whole, well, Reshma, we all know she's awesome. So it's great to actually have a Fast AI community person there too. And so, but yeah, I kind of tried to pull together people from, as many geographies as possible and as many areas of expertise as possible. And, the kind of the global community helped me find papers about everything, about, how different materials work, about how droplets form, about epidemiology, about case studies of people infecting with and without masks, blah, blah, blah. And we ended up, in the last week, basically, we wrote this paper. It contains 84 citations. We basically worked around the clock on it as a team. And it's out. And it's been sent to a number of, some of the earlier versions 3 or 4 days ago, we sent to some governments. So one of the things is in this team, I try to look for people who were working closely with government leaders, not just that they're scientists. And so this went out to a number of government ministers. And in the last few days, I've heard that it was a very significant part of decisions by governments to change their guidelines around masks. And the fight's not over by any means. In particular, the UK is a bit of a holdout. But I'm going to be on ITV tomorrow and then BBC the next day. It's kind of required stepping out to be a lot more than just a data scientist. I've had to pull together, politicians and staffers. I've had to, hustle with the media to try and get, coverage. And, today I'm now starting to do a lot of work with unions to try to get unions to understand this. It's really a case of like saying, okay, as a data scientist, and in conjunction with real scientists, we've built this really strong understanding that masks, are this simple but incredibly powerful tool that doesn't do anything unless I can effectively communicate this to decision makers. So today I was, on the phone to, one of the top union leaders in the country, explaining what this means. Basically, it turns out that in buses in America, the air conditioning is set up so that it blows from the back to the front. And there's actually case studies in the medical literature of how people that are seated downwind of an air conditioning unit in a restaurant ended up all getting sick with COVID-19. And so we can see why bus drivers are dying because they're right in the wrong spot here and their passengers aren't wearing masks. So trying to explain this science to union leaders so that they understand that to keep the workers safe, it's not enough just for the driver to wear a mask, but all the people on the bus need to be wearing masks as well.
Yeah.
So, all of this is basically to say...
oh my God. This data is going to make me... I heard recently, you don't truly understand numbers or math or science until numbers can make you cry. And I guess I shouldn't be ashamed. It feels kind of shameful, but I read the most recent Scientific American article on the things happening in the United States where they endorse Joe Biden after going 175 years without saying anything political, especially not just outright endorsing a candidate, really trying to be as apolitical as they possibly can. Just after 175 years of that, endorsing a candidate, and they gave the reasons why, and it had all these numbers in there, and it's I really understood what those numbers mean, and these were all numbers for what Joe Biden will be able to do, what's in his plan, what he's planning to take, and just it struck me if he doesn't get elected, all this data, all these numbers aren't going to come true, and we're going to live 4 years at least, maybe even longer than that, with none of the numbers that were in that article actually being enacted. We're going to have those numbers at zero. And we're going to continue to have the numbers we see now every day, rising deaths, economic destruction. Those are the numbers that are going to be incrementing. So it's it's really been hard on me these last few weeks, and I really like what Jeremy has done here, though. I would watch Lex Friedman a bunch, and after a while, it's okay, podcast, Joe Rogan wannabe, what have you actually done to claim your scientist title? Because he always goes out and about being a scientist, but so seeing his name on a paper like this really gives him a lot credibility in my mind, because I would only see him like doing like silly things like playing a guitar in a self-driving car, like. But it looks like he does do some really impactful, substantial work. So that's really kind of I'll probably be watching some more of his stuff because of that. Because after a while, I was just like, okay, well, what do you have you actually done anything, or are you just wearing science like like it's a a fancy sport jacket or something? That kind of bothers me when people do that. But yeah, so it's been pretty. Yeah, so let's just keep watching. And we only got a minute left, so we'll finish the video in 1 minute.
You know, as data scientists, I think we have a responsibility to study the data and then do something about it. It's not just a research, exercise. It's not just a computation exercise. What's the point of doing things if it doesn't lead to anything? Yeah. So next week we'll be talking about this a lot more. But I think this is a really, to me, kind of interesting example of how digging into the data can lead to really amazing things happening. And in this case, I strongly believe, and a lot of people are telling me they strongly believe, that this kind of advocacy work that's come out of this data analysis is already saving lives. And so I hope this might help inspire you to take your data analysis and to take it to places that it really makes a difference. So thank you very much, and I'll see you next week.
Yeah, that was pretty cool, that last part. I really didn't, unfortunately, get a lot out of this lesson. I think I don't know, like, there's just a lot coming at me, and, as I've said, is this, I don't know how much this can benefit me. Is somebody gonna, hire me as a principal machine learning engineer tomorrow? Probably not. Principal network engineer? Oh yeah, give me a call. Like, I've almost got my JNC IESP, I've got 6 years of experience, going on 7, like, of like actual experience. I worked for the second largest ISP in the United States, and now I'm working for a similar, Fortune 500 company. Yeah, I'm working on the networking for this project. I'm a contractor right now, but like, this is more like enterprise too. So I'm like seeing both sides of it. I worked in an ISP. Now I'm getting experience with enterprise. Like, it's like basically what I'm trying to say is that I'm just not sure if I'll get back the time I put in studying machine learning. That's kind of a lesson I've learned the hard way when because I initially wanted to be a professional musician, and I just realized, like, I can practice as hard as I want, and at the very best, I won't get back anywhere near something more valuable than the effort I put in. And that's been pretty much the opposite with a lot of like networking computer stuff. It's like I studied pretty hard in well, let's put it this way. All of my studying has been very dedicated, very hard, intensive, but my degree lasted 2 years. I didn't do a 4-year degree with a master's and a PhD. I just did a 2-year degree, studying with absolute intensity as hard as I could, but for only 2 years, and it completely changed my life. All right, so yeah, let's do the questions now, and let's I guess I don't know if cheat is the right word, but let's use the the answer key, and we'll just think about the answers instead of the questions. That's lesson 3. What about lesson 1? Or sorry, lesson 4. Why can't we use accuracy as a loss function? Let's see here. Accuracy. Okay, so we're at the pet breeds. Yeah. Oh, okay. Looks like it's not in this chapter. Um, is it a multicat? Okay, well these are... I wish I had... Here, let's go to history and then back to the questions that... okay. I mean, showing my internet history is probably not a good idea, but it's let's see here. So, well, you know what? I can filter it. So let's say fast AI. Yeah. Just showing my internet history of fast AI is a good idea. Oh man, I'm getting hot. A while ago I had to use, like a few videos ago I had to use an ice pack. I got so hot. Okay, well, alright, well let's look at the questions from the last one because I used a special guide to answer them. Alright, and then we'll see if that guide has a section that I can use for this next one. Oh my god. Okay, well, I was literally just looking at something a while ago and I can't find it now. Ah, here we go. Yeah, so here's the chapter 2 solutions. Let's see if we can get the chapter whatever solutions, chapter 6 or something. I don't even know. Okay, here we go. So this is for chapter. Okay, well, not this chapter, unless he went into some of it. It was for like cat breeds. So it's not chapter 6. I think it's chapter 5. Yeah. All right, and then yeah, I realize, okay, it's not the best way to learn, but it is the best way to save time, and I think I want to do a swim today. Like there's other things I want to do. Okay, so why can't we use accuracy as a loss function? Oh, so I can draw a sigmoid function. It's like a um, um, let's see here. So yeah, it's almost like, oh, what's a way to draw a sigmoid function? I mean, it's kind of like the letter S, but not quite. Um, yeah, it's kind of like a letter S, but if you tug on the top and you tug on the bottom until it's like smooth, and then of course it's not going to be going to the right, the slope is going to be going, yeah, so it's kind of like the letter S. All right. Well, I'm having trouble with these questions. I want to take a break. Right now we're coming up on 2 hours, so I'm gonna take a break and then yep. So I'll be back. All right, we got a red circle again. I'm back. I took a super long break. I don't know. I've just been having trouble finding the answers to these questions through any like time efficient, quick way. I mean, I want to participate in the class. It's just it is a lot of a pretty big time commitment. So let's see if we can look at what Vue does in PyTorch. Let's try not to go through the Yeah, we don't need to go through it in order, the questions in order. Let's just try to pick out the easier ones, get those done, and then go back through and try to get the more difficult ones. So basically, we're just gonna, yeah, we're gonna go through everything out of order, and we're going to, and then we're going to come back. Okay, so it looks like not all of the answers are going to be in chapter 5, so I'm going to open up multiple chapters. Okay, so we'll open up chapter 2 maybe, chapter 4, and chapter 3, and let's see if there's anything about PyTorch. Now, I don't think it'll be in chapter 2. Yeah, I don't see anything in there. Let's see chapter 4, and I already checked chapter 5. Oh, so PyTorch is just mentioned a bunch of times. I bet you it shows up in here because of how often PyTorch is mentioned. Alright, so let's try searching for the word view. Ah, here we go. We can do this, okay, so I can close the other ones now. I know that the answers are going to be in chapter 4. We can do this using view, which is a PyTorch method that changes the shape of a tensor without changing its contents. So, okay, I can't see it there, so let's look for it. Ah, okay. So what does view do in PyTorch? It changes the shape of a tensor without changing its contents. All right, so I'm feeling pretty good now that I know where the answers are. I think I can continue with this, but before I do that, I'm going to take a quick break. I'll be right back. All right, we've got a red circle again, so let's get all these questions done. So why can't we use accuracy as a loss function? Okay, so recall that a metric is a number that is calculated based on the predictions in our model and the correct labels in our dataset in order to tell us how good our model is. For instance, we could use either of the functions we saw in the previous section, mean squared error or mean absolute error, and take the average of them over the whole dataset. However, neither of these are numbers that are very understandable to most people. In practice, we normally use accuracy as the metric for classification models. Oh, okay. Well, why can't we use it as a loss function? Okay, but in order to calculate a metric for overall accuracy, we will need to calculate the distance to the ideal 3 for every image in the validation set. How do we do that calculation? Okay, but there is a better way. I don't know why we can't use it as a loss function. Ah, here we go. A very small change in the value of a weight will not actually change the accuracy at all. This means it is not useful to use accuracy as a loss function. If we do, most of the time our gradients will actually be 0, and the model will not be able to learn from that number. Excellent. So let's draw a sigmoid function. What is special about its shape? So yeah, so in mathematical terms, accuracy is a function that is constant almost everywhere except at the threshold 0.5. So its derivative is nil almost everywhere and infinity at the threshold. This then gives gradients that are 0 or infinite, which are useless for updating the model. Instead, we need a loss function which, when our weights result in slightly better predictions, gives us a slightly better loss. Okay. And accuracy does not do that. Okay, so the next question. Draw the sigmoid function. What is special about its shape? Yeah, so here's the sigmoid function. I guess, if I were to draw it beforehand, when I was trying to do these questions, I said it looked like the letter S, but stretched out, kind of like if you would scrunch these together so that this starts going the other way, you get a letter S. So I think I was right about that. I'll just include a screenshot in the questions. Okay, and then the next part will be what is special about its shape. So it takes any input value, positive or negative, and smushes it into an output value between 0 and 1. It's also a smooth curve that only goes up, which makes it easier for SGD to find meaningful gradients. All right, so what is the difference between a loss function and a metric? Oh, here we go. So as we've seen we need gradients in order to improve our model using SGD. And in order to calculate gradients, we need some loss function that represents how good our model is. That is because the gradients are a measure of how that loss function changes with small tweaks to the rates. Oh, and I don't see anything about a metric. All right, let's search for metric. Okay, so a metric is a number that is calculated based on the predictions of our model and the correct labels in our dataset in order to tell us how good our model is. So that's okay. And then let's learn about what a loss function is. So a loss function returns a value based on a prediction and target, where lower values of the function correspond to better predictions. For continuous data, it's common to use mean squared error. All right. So what is the function to calculate new weights using a learning rate? Okay, so stepping with a learning rate, deciding how to change our parameters based on the values of the gradients is an important part of the deep learning process. Nearly all approaches start with the basic idea of multiplying the gradient by some small number called the learning rate. The learning rate is often a number between 0.001 and 0.1, although it could be anything. Often people select a learning rate just by trying a few and finding which results in the best model after training. We'll show you a better approach later in this book called the Learning Rate Finder. Once you've picked a learning rate, you can adjust your parameters using this simple function. This is known as your stepping parameters using an optimizer step. If you pick a learning rate that's too low, it can mean having to do a lot of steps. But if you pick a learning rate that's too high, it's even worse. It can actually result in the loss getting worse, as we see. Oh, you know what? I wonder if now are these the correct questions? Because let me go to my Google Drive. Okay, and then let me change over to, yep, my other one. And now let me look at the questions from the previous lesson. Lesson 3. Now, do we have anything like sigmoid data learner? Okay. Data loader, okay, nothing like that. I don't know, I just, for some reason I'm questioning whether or not I'm being asked questions relevant to lesson 4 or lesson 3, because I thought I remembered seeing that in the lesson 3 video. Okay, so right now we're on lesson 4, not lesson 5, which is the interesting one. Yep, so these are the correct questions. Let's see what the questions were for lesson 3. Okay, lesson 3, yep, you can see the questions are quite a bit different. Okay. So what does the data loader class do? Okay, so a data loader can, so it takes any Python collection and turn it into an iterator over many batches. Okay, write pseudocode showing the basic steps taken in each epoch for SGD. Okay, so I believe there's 7 steps. Yeah. So I think when they say epoch, they mean step. Yeah, so there are many different ways to do each of these 7 steps, and we will be learning about them through the rest of this book. These are the details that make a big difference for deep learning practitioners, but it turns out that the general approach to each one generally follows some basic principles. Here are a few guidelines. Okay, so each epoch, I guess I'm confused as to what they mean by, yeah, so we just decided to stop after 10 epochs arbitrarily. Okay, so they just want to see basic steps taken within an epoch. So I think those 7 steps aren't an epoch. I guess I'm not sure what an epoch is. Oh, okay. So here's the epoch. Okay, so here's the 7 steps. So the first step is to initialize the parameters. Then calculate the predictions, calculate the loss, calculate the gradients, step the weights, see if the loss has improved, show, okay, and then repeat the process. So the loss is going down just as we hoped, but looking only at those lost numbers disguises the fact that each iteration represents an entirely different quadratic function being tried on the way to finding the best possible quadratic function. We can see this process visually if, instead of printing out the loss function, we plot the function at every step. Then we can see how the shape is approaching the best possible quadratic function for our data. Okay, so we just decided to stop after 10 epochs arbitrarily. In practice, we would watch the training and validation losses and our metrics to decide when to stop, as we've discussed. Okay, so I'm going to pause it and clean up my disk a little bit. I've got an empty bag on it that's kind of bothering me, so I'm going to go throw it away. Alright, so I'm back. There's no longer garbage on my desk. There's a bunch of things on my desk that shouldn't be there, but oh no, there's garbage on my desk still. Damn it. Okay, but I'm okay with that. Yeah, it's just I bought something and like the plastic thing it came in is like still okay. Okay, but now they're saying to write pseudocode showing the basic steps taken in each epoch for SGD. So let's do that. And I think, yeah, so they're talking about these 7 steps here. So let's write some pseudocode. Yeah. So let's first start. Yeah, let's follow this end-to-end example. So here we go. Oh man, I might need an ice pack again. I mean, I guess I could just put the air conditioning on early. Usually it goes on a little bit later. Like I'm supposed to, I have it heat up like right now to incentivize me like going outside, because the idea is I don't want to like spend all day indoors, go outside, and then just have it be so hot that I just need to immediately go back inside. So the solution to that was to just have it, just turn off the air conditioning every day after work, and and just have it heat up naturally. So if I leave the apartment, that I don't get this big like heat up that makes me just want to go back inside. But I don't know if that's effective, because it's like whether or not I leave the apartment has more to do with like habit than desire. And when I don't leave the apartment, you know, I'm sweating so badly, I need like an ice pack or something. So I think, you know, I want to, I mean, it'd be great to get outside, to be honest, but I definitely want to finish this project. So I think I'm going to finish writing down the steps. Okay, and then we'll write some pseudocode after I turn on the air conditioning. So I'll be right back. Okay, and I changed into a T-shirt too. It does have a, I think I like did some baking, and I got some flour on my, so it's like a stuck on like you know, it's a kind of shirt stain that is just going to take some advanced laundry to get out. So I kind of haven't been wearing this shirt lately because I just sending it through the washing machine isn't gonna get this stain out. So, but yeah, it'll be just fine to wear for now. That long sleeve shirt was just too hot. All right, so now let's write some pseudocode. So the pseudocode, write pseudocode showing the basic steps taken in each epoch for SGD. So step 1 is going to be to initialize the parameters. So, I mean, let's just use the code that they had. Okay, so it's going to be these 2 lines here. Okay, now step 2 is going to be calculate the predictions. Okay, so then step 3 is going to be calculate the loss. All right, step 4, calculate the gradients. Lost that backward, and then we multiply the gradients. Yep. All right, so step 5 is going to be step the weights. Step 6, repeat the process. Alright, and then step 7 is going to be stop. Oops, there's no code for that. Okay, so create a function that if passed 2 arguments, returns, okay. So what is special about that output structure, data structure? Okay, so I've got IPython on my computer, so I will open it. Okay, and now we'll write a function that will take 2 arguments and, oh, that's interesting, okay. Oh, you know what, that's not going to be too hard. Yeah, that'll be pretty easy. Okay, so def combine list list param and then string param. Yeah, and that's one thing to know is that when you're defining a function, the things you put inside the parentheses are called parameters. But when you're calling a function, when you're running the function, the things you put in the parentheses are called arguments. So it's kind of a, not, most people probably would not call them the correct thing. But me personally, like, I always try to call them the correct thing because it just makes it more clear whether you're talking about defining a function or calling a function. Okay, so yeah. Oh, okay, we could probably do this in a list comprehension actually. So let's do return, and then here's going to be our list comprehension. So we're going to return, and it's going to be a tuple. Yep, like that, and then it's going to be and let's say I for I in list param well, can I do something like this? Let's see here, for I, j, for j. See, I wish I could do this, but that's not going to work. That's going to be a syntax error. In Python 2, I could do this. But I'd have to do oh, sweet, okay. I think that's gonna work. I don't know why it worked now. I'm pretty sure I've tried that sort of thing before and it has not worked. Oh. List object is not callable. This object is not callable. Oh, you know what? I've got to do list object is not callable. Oh, I don't know why I'm using Y here. List object, okay, but I still have the issue. Okay, well let's see this. So map. So let's do map 1A. Okay, we'll do I, J, for I, J in map. Okay, list object not callable. So let's see what happens if this is not a list object. Int object is not callable. What if we've got two strings? String object is not callable. But what if I do this? None type object is not callable. Too many values to unpack. Expected to. Okay. Expected 2 values. Okay, well, Okay, well, I don't understand. I don't get why this doesn't work. Too many values to unpack. Expected 2. What expected 2? Okay, I mean, I knew that wouldn't work. Let's see here. So let's do I for I in 1, 2, 3. Yeah, like that's gonna work. But what about J for J in, so I could do this. But I need, instead of enumerate here, like I thought map, like I thought you could do this. I mean, you can do it in Python too. Yeah. How do I do that? X range. Oh, zip. Okay. Oh, okay. Yeah. Actually, I knew that. I knew that. Wow. Okay. No, I knew that. I've done that before. Ah, crap. Wow, okay. Yeah. Okay, wow. Yeah. Oh, ouch. I knew that. Ouch. Alright, I feel dumb for not knowing that. I mean, I knew like what the answer was going to look like. I just didn't know that the function was zip, even though I've used it before. And not knowing that is kind of embarrassing to me. Um, oh, where was this even? Oh, here it is. Yeah, because I already answered question 8. I started with question 8. So yep, it's zip here. So I don't know. Do they call out zip in the book? Oh, they do. Yep. So yeah, I knew that. I've used it before. In Python 2, it's the map function. So map kind of works like zip, but you've got to pass it a third argument because the first parameter is a function, but you can include none and just not have a function and just have it go through parallel. So it's cleaned up and it's nicer in Python 3 as long as you know that you've got to use zip instead of map. All right, so what are the bias parameters? And in a neural network, and why do we need them? Oops. Okay, so the weights and biases of a model. The weights are the W in the equation W equals X plus B, and the biases are the B in that equation. Okay, so I'll include all of this in my answer. All right, so what does the @ symbol do in Python? That's, oh no, I know what this does. I know what it does. It's a decorator. So it like you can say like a really good way you can use the @ symbol is to document things. But if I do help @ symbol, oh shoot, what about just help and then what if I do it there? Ah, okay. Yeah, so now we can see, yeah, so it's a decorator. And then we need a dotted name. Yeah, so I'll show an example of, oh yeah, here's the, okay. So this is just help on functions, but I'll try to I'll get an example of what this is. Okay, so what you can do is you can do def hello world, and then you can do return hello world. Okay, and then you can do @ hello world. I think print hello. Oh, wait. No, I thought it was. Invalid syntax. Okay, well, I don't know. I don't know how to use these very well. I never used them, but from what I understand, they're really useful for like logging. Oh, and that's interesting. Oh, it's matrix multiplication. Okay. I thought it was, I didn't know it was used for that. I thought it was used for, um, I thought it was used for like, generators. Yeah, like, yeah, like, so, oh, I guess I was completely wrong about that. Yeah, what is the at symbol? Yeah, yeah, yeah. Yeah, oh, not generators, decorators. Yeah, so this is a good, I think this is a good example. Let's run it and see if we can make sense of it. Oh, um, looks like he gave the example in Python 2. I'm sure it'll be the same. Okay. So, oh my god, this is making me hungry for pizza now. Okay, so let's just type out everything. There's a great book, Learn Python the Hard Way, and he says just type it out character for character. Don't worry about it, what it means. Just stare at it, and eventually you'll get used to seeing it, and then that's pretty much the first step to actually learning it. Learning it without being used to actually looking at it is uh, more difficult than learning it with having seen it, a million times before. And I think we can all attest to that. It's like if you're around it, you see it every day, you grew up with it. It's really not that hard to learn it. I mean, look at, how hard was it to learn to speak English for somebody who was born here? Like, yeah, there's challenges, but compare that with how hard it is to learn a foreign language. Oh, god damn it, why can't I? Okay, well, I guess I can't hit the enter key. Okay, so now we've got an instance of pizza here. So when we use the at instance of pizza, which in our case is just named pizza, and then define a function, the function gets passed into topping because we've got self dot toppings dot append, and then so this is basically what we're going to do is we're going to this topping here variable, that's going to be our function. So it's almost like we're doing this here. So it's almost like we're doing pizza dot call, and then def cheese return cheese. So it's almost like we're doing that. Let's see if this works actually. No. So you can see it's kind of a nice way to do it because you can't define a function while you are passing it, or while you are passing it into another function. It has to be predefined. So of course you could do def cheese and then return cheese, and then you could probably do pizza call, oops, there's gonna be two of those, call, and then maybe this will work. Now, see, and that doesn't even work because we're not even passing the function in here. We're passing a cheese. So the only way you can actually pass a function into a function is through this syntax. So instead, I can do pizza, and then I can't do cheese like this. That's not going to work. But what I can do is say, okay, I'm going to pass a function into you, pizza. I'm going to pass you into this special call method. So in order to do that, I've got to define the function. Okay, and now that special call is going to wait. Yeah, so now it's going to because we can see here self.toppings.append, so self.toppings, so yeah, so I think this part does the return self.toppings, so without that in there. So let me try to do it using my classic. So class example, and then say object, because they have it, and we'll say init, oh sorry, definite. We'll say self. Oh, do we need self? Yeah, we do. We do doing that. Okay. Okay, and then we'll do self dot my list equals a blank list, and then we'll do def call, and then it'll be self, and that'll be my list, right? No, it will be your func. Yeah, your function. Okay, and then we're gonna do self dot my list dot append. Okay, and then it's going to be calling your function. Yep. Def Okay, so we're going to do test equals example. Okay, and then we're going to do test def try something, return you did something. Oh, I see. I accidentally did toppings here instead of my list. God damn it. Okay. Well, anyways, I got a handle on it. So let's move on to the next question. Oh, it's not generators, it's decorators. Okay, what does the backward method do? And it's a method, so it belongs to a class. I'm not sure which class it belongs to. Okay, so backward refers to propagation, which is the name given to the process of calculating the derivative of each layer. Okay, why do we have to zero the gradients? Oh my god, I'm not even halfway done. I'm not even close to halfway done. Okay, that's disturbing. Okay, so loss.backward actually adds the gradients of loss to any gradients that are currently stored. Okay, what information do we have to pass to learner? So training and validation data loaders. Oh. Yep. So here's our answer. What information do we have to pass to learner? So we have to pass data loaders, the model, the optimization function, which will be past the parameters, the loss function, and optionally any metrics to print. Okay, so show Python or pseudo code for the basic steps of a training loop. Okay, yeah, so this is it. Oh, no, this is it. Yeah. Okay. So what is RELU? It's rectifier linear unit. Oh, so we gotta draw a plot for it from values -2 to +2. Okay, well that's the one that is given, so include that screenshot. Okay, what is an activation function? So the three lines of code that we have here are known as layers. The first and third are known as linear layers, and the second line of code is known variously as non-linearity or activation function. So amazingly enough, it can be so it's a non-linearity. Okay, so it's a torch module that does exactly the same thing as the freelove function. It's the same thing, but a torch module. They are the same thing, but NN is a torch. RELU is a torch module. The universal approximation theorem shows that any function can be approximated as closely as needed using just one linearity. So why do we normally use more? I don't know. Okay, we already know that a single nonlinearity with two linear lines is enough to approximate any function. So why would we use deeper models? The reason is performance. With a deeper model, that is one with more layers, we do not need to use as many parameters. It turns out that we can use smaller matrices with more layers and get better results than we would get with larger matrices and few layers. Oh, I'm actually kind of making some progress now. Alright, so why do we first resize to a large size on the CPU and then to a smaller size on the GPU? Let me make sure the video is still, okay, the video is still recording. We're almost at the 3-hour mark. So yeah, let's try to finish all these questions, man. I think I can do it. I think I saw it. Okay, so another good reason. Another good reason for using mini batches rather than calculating the gradient. Well, that's about, let's hear, size. Okay, I think this might be from the next chapter or something, because yeah. So let's go back to the fast book. Let's go to chapter 5, and let's see if CPU is mentioned. Ah, yeah. So these are from the next chapter. Okay. Okay, so we need our images to have the same dimensions so they can collate into tensors to be passed to the GPU. We also want to minimize the number of distinct augmentation computations we perform. The performance requirement suggests that we should, where possible, compose our augmentation transforms into fewer transforms to reduce the number of computations and the number of lossy operations, and transform the images into uniform sizes for more efficient processing on the GPUs. The challenge is that, if performed after resizing down to the augmented size, various common data augmentation transforms might introduce spurious empty zones, degrade data, or both. For instance, rotating an image by 45 degrees fills corner regions of the new bounds with emptiness, which will not teach the model anything. Many rotation and zooming operations will require interpolating to create pixels. These interpolated pixels are derived from the original image data, but are still of lower quality. To work around these challenges, Presizing adopts two strategies that are shown in this chevron. Resize images to relatively large dimensions, that is, dimensions significantly larger than the target training dimensions. Collapse all the common augmentation operations, including a resize to the final target size, into one, and perform the combined operation on the GPU only once at the end of processing, rather than performing the operations individually and interpolating multiple times. The first step, the resize, creates images large enough that they have spare margin to allow further augmentation transforms on their inner regions without creating empty zones. This transformation works by resizing to a square using a large crop size. On the training set, the crop area is chosen randomly and the size of the crop is selected to cover the entire width or height of the image, whichever is smaller. In the second step, the GPU is used for all data augmentation, and all the potentially destructive operations are done together with a single interpolation at the end. Yeah, I don't know the answers to this. Oh. Oh, that's your batches though. That's not the size. Um, yeah, I have no idea. I mean, I'm tempted to just stop there anyways, because I mean, I don't have that many to go, but I'm losing it. Yeah, I might do a part 2. Yeah, I think I'm gonna stop there because that's about the next chapter anyways. So I think this is gonna be part 1 for this video. So um, I'll try to get a part 2 done sometime tomorrow. And so stay tuned for that. Thanks for watching.